So Professor Tim Byrnes is joining us from Shanghai in China, and is going to talk to us about quantum information science, current trends, and future opportunities. Professor Byrnes is currently an assistant professor at NYU Shanghai, the New York University campus in China. He's a theoretical physicist working on various topics in quantum information science, particularly in the areas of atomic molecular optics, quantum information theory, and condensed matter physics. He started his career in high energy physics in Australia and then moved to Japan, where he worked on quantum simulation, specifically in the context of studying many body quantum systems. After moving to Shanghai, he focused on using cold atom systems for a novel type of quantum computer using atom chip technologies. You've heard a little bit about quantum computers early today, but it's exactly about this research that we'll hear about now. So without further ado, Tim, the floor is yours. Thanks.
Okay, so thanks very much for the introduction. And so let me first say that I'm super excited to be part of this wonderful meeting. So it's a great pity that I can't be there in person to meet you all for obvious reasons. But so from what I can see, the organizer put together a really great meeting. So I'm glad, I think everybody is enjoying it. And so I want to thank the organizers for putting this all together and this opportunity to speak here. So should, the screen is already shared, is it? Let me just.
Probably it unshared when I shared mine. So right now you're not sharing a screen.
Oh, right now I'm not sharing? Okay, let me start that again. Okay, how's that?
Yeah, now it's fine.
Okay, great. Yeah, so what I thought I would talk to you today is a little bit about the field that I'm working in, which is quantum information science. And so this will not be like a really hardcore physics talk. I'm not going to go into all the details of all the things that we've been researching, but I thought I would give you a sort of a grander overview of what's happening in the field and all the sort of exciting developments that we're now seeing in this area. And another thing which I thought I would do is just to talk a little bit about how I came to be working in this particular field, because I think many of you are sort of junior researchers, you're undergraduate students, graduate students, and so I thought maybe hearing some stories about how I ended up in this position might be maybe of interest, and I'll of course talk a little bit about things that we're doing. Okay, so what is this field of quantum information science? Maybe a lot of you are already familiar with this, but let's recap. So of course we know that many of the technologies today are sort of underpinned by basically, laws of physics, obviously. So all the inventions that we're very familiar with, such as computers, planes, automobiles, all these things, of course, rely on the laws of classical physics. But we also know that quantum physics is an area of physics where it actually sort of goes beyond classical physics. So quantum physics includes classical physics, but there's certain things in quantum physics that you obviously can't do in classical physics, such as superposition, entanglement, things like this. So the natural question in terms of technology is, well, what kind of new technologies can we make in terms of taking into account of quantum physics? So there are already some kind of quantum inventions, as I would call them. So things like MRI machines, lasers, high temperature superconductors, all these things really require quantum physics to explain their working. But as somebody working in this field, we think there's a lot more really waiting to be discovered. So we're trying to figure out what is really on the horizon after these types of invention. So type of technologies that people are looking at are things like quantum key distribution. This is secure transmission of information. Of course, this is extremely important in today's age where we're transmitting all kinds of information through the internet. And so we really need to be able to secure that information so that other people do not read messages that we're transmitting. Quantum metrology, this is basically precision measurements. So this is a picture here of, say, a gravitational wave device. And so in the latest gravitational wave experiments, now they are including sort of enhancements that kind of ideas that have been generated in this field of quantum information. We're using squeeze states to have even more precise measurements of the detections that you want to make. So in this case, gravitational waves. Quantum simulators, I'm going to talk about this a little bit later on in the talks. This is simulation of complex materials, and of course, quantum computers. And so this is trying to make computers with that go beyond classical physics. So maybe one of the most sort of exciting developments that has been happening in this field is really this kind of commercialization of this area. And so there are, major companies like IBM, Google, and so forth, who are now really actively involved in quantum technology research. And actually, there are so many new companies that are coming up all the time that it's really hard to keep track of them. But one major frontier is in terms of developing quantum computing technology. And so the major players are companies like IBM and Google, where they're now pursuing quantum computing technologies. They're up to something like 50 or so qubits. That's sort of the bar at the moment as of 2021, but of course it keeps on going up every year. And there are many different companies using different technologies to work on quantum computers. So one of the, I think, the real breakthroughs in the last few years has been this demonstration of quantum supremacy. So this came out 2 years ago now, in 2019, and this was led by the group, of course, so famously, this is the quantum computing system that was built by Google, but actually this is coming from the line of research that John Martinez did at UC Santa Barbara. So basically this demonstration was the first time that you could actually perform some kind of quantum mechanical process that was really fundamentally impossible to simulate on a classical computer. So the type of circuit that they did was actually like not a very useful circuit. It was actually a quantum random circuit where they just kind of put together random gates. And so it obviously doesn't really do any important kind of task, but nevertheless, if you were to try and simulate this same thing on a classical computer, then, well, at least in this paper, they claimed it would take something like 10,000 years. Later on, people came up with more efficient algorithms, but still, actually, it's very difficult to simulate on a classical computer, meaning that it still is a demonstration of quantum supremacy. So that was 2019, but a couple of years before that, there were really some big breakthroughs also, this time by the Chinese team. So as I was introduced, I'm actually living in China, so this is, of course, very interesting to me. But the group at the University Science Technology China, they managed to actually launch a satellite with quantum capabilities. And so basically what this means is that they could shoot entangled photons in sort of two different directions. And so here's a picture on the top here where one photon is sent to Shanghai. That's actually where I'm right now. And another one goes to Beijing. In fact, I think the main experiments were done in observatories that were more in rural areas, because obviously with light pollution, it would be virtually impossible to do this really in Shanghai. But what they demonstrated was that they could distribute entanglement across 1,200 kilometers. And this was really a big deal at the time, because the previous record before that was about 143 kilometers. So this was demonstrated off 2 islands off the coast of Africa. And they had 2 observatories on top of these 2 islands. And you need observatories basically to do this kind of experiment, because you've got like one photon which is traveling 143 kilometers, and so you really need some really good optics to perform your experiment. And they did this across these islands not because they want to go on a nice holiday in some tropical islands, but because you really need these observatories to be quite high in altitude, because the curvature of the Earth actually kind of blocks your line of sight, right? So they managed to do quantum teleportation over 143 kilometers, which is already super impressive as far as I'm concerned. But basically, the Chinese team could now do this to a much larger distances, so 1,000 kilometers. So this is now starting to look like sort of more like inter-country types of distances rather than sort of intercity types of distances. And why were they able to achieve this? Well, basically, the trick really is to go to space. And the major problem in an experiment like this is that photons get absorbed by the atmosphere. So, because you're just sending like a single photon, it's easily absorbed by some dust or something that's in the atmosphere. But of course, if you go to space, basically photons can travel basically forever. So, because the atmosphere is only about, say, 30 kilometers thick, even if you send 2 photons down, they only have to go through about 30 kilometers of atmosphere on either side. And so that's actually less than this 143 kilometers. So by going to space, you get a massive advantage. And of course, I mentioned the curvature of the Earth. Of course, you don't have any problems like that. So now people are really seriously thinking about making a quantum version of the internet, where you have nodes which are located at various locations, and entanglement, which would be distributed using this kind of satellite technology. And so this was some real kind of breakthroughs. And the fact that basically China was the first country, and basically I have no particular vested interest in which country. I'm only interested in advancing technology. But the fact that some groups were really making some big progress spurred some major changes in funding. So you may have heard that in 2018 there's a major initiative in the US where they really want to push quantum technologies, and so this was signed by Donald Trump at the time. So now we're sort of in this age where we're going where there's a huge amount of sort of funding available, both from sort of government sectors, but also sort of from the private sector, as I sort of already mentioned at the beginning. So there's sort of articles appearing saying that there's sort of a quantum gold rush where anybody that was sort of involved in sort of quantum physics research are now just frantically setting up companies in order to cash in on this kind of quantum interest in quantum technologies. And you can sort of see the amount of interest that's changed in the last few years. So D-Wave, so back in about 2000, D-Wave was the first commercial company to build, or their mission was to build a quantum computer. But in the early days, actually, I think they were somewhat unfairly ridiculed for attempting to go down this path. All the people in academia were saying, they can't be taken seriously and so forth. But 10 or say 12 years later, there's a massive number of different companies that have emerged on the scene who are now also pursuing the same approach. And so even though at the beginning, I think D-Wave was somehow, they weren't really looked upon favorably, at least in the academic world, but now I think generally this is now the common accepted practice. So amount of funding has also increased drastically over the last several years. So in the early days, perhaps these quantum companies were only getting, say, a few $1 million at a time, but now we're in the realm of hundreds of millions of dollars, and now we're sort of emerging on this sort of new realm of where these companies are starting to be funded in the billions of dollars. So IonQ here to the right is another quantum computing company that was set up by Chris Monroe. He's one of the leaders in ion trap quantum computing technology. And so this company is now really expanding on a huge scale. They were only set up a couple of years ago, but already attracting huge amounts of money. So yeah, there's many different types of quantum technology companies, not just in quantum computing, but in all kind of areas. There are sort of quantum encryption. So this has been around for some time. So ID Quantique, this was one of the early types of quantum cryptography related companies. They manufacture things like QKD devices so that you can secure communications, and even sort of quantum software companies. So even though quantum computers don't really exist on a very large scale, if you're a theoretical physicist such as me, then you sort of you can't build a quantum computer yourself, but what you can do is you can sort of aim to be maybe the next Google or Microsoft of the quantum computing world. So so there's real sort of activity in this area. But let me sort of step back a little bit and ask, so, how did we get to this point? Because actually, this was not always the case that quantum computing was such an area of interest. And certainly when I got into the field, this was actually not the case at all, as I'll sort of explain in the next few slides. So if we step back to when I was a PhD student, this was sort of in the mid-90s. As you might tell from my accent, I'm originally from Australia. I went to the University of New South Wales in Sydney, and I was a third-year undergraduate student, perhaps like many of you are now. And in Australia, in the last year of your undergraduate studies, you do two research projects, in fact, one per semester. And the way that you choose it is you simply look through a handbook and you just sort of pick something that looks interesting. And so there was one project that I remember that was on the foundations of quantum mechanics. And so I decided to choose that. So I went to my professor that I chose. And in the first day, he gives me this kind of article. This is a popular science article from quite a long time ago, I think even the 70s. But I really like this article. It's quite a really well written kind of piece, and it kind of really gets to the core of why sort of quantum mechanics is so strange and wonderful. And so what this is talking about essentially is Bell's inequality. And perhaps, I'm not sure if this is taught in sort of undergraduate courses these days, but in a nutshell, basically what this is about is if you have, say, a setup such as what I draw here, we often call sort of two parties in this field, Alice and pictures that I have there, and say we have some kind of random source of particles which are being sent to each of these detectors. And this could be, any kind of random source with, potentially a huge amount of information. But just for the sake of simplicity, I'm just going to picture them as like red and blue balls going into these detectors. So these might be correlated in some way. And Alice and Bob, they both have some kind of detectors to detect these particles. And depending on what kind of particle they have, there's some kind of rule that they output some value, some binary value of plus and minus 1. So this rule is somewhat arbitrary. And there are also two settings on the device so that you can switch between two different rules for outputting, 1 or -1, depending upon what particle that you detect. And so this is a totally classical problem, right? So you can say for any kind of classical distribution for this type of setup, and the key thing here is that Alice and Bob, they both have to make their judgments sort of independently. So they can't kind of conspire, get together, and then, you know, give some kind of output. They really have to make their argument purely based on the results that they have. So there's this particular inequality, famous inequality called the CH-SH inequality, named after their inventors, Clauser-Horn, Shimoni, and Holt. And you can make a statement about probabilities of this particular setup. So that's the classical case. But for the quantum case, of course, you can have entangled particles. And entangled particles have a very kind of similar setups where you can make measurements where you can output binary values. So if you've got some qubits, then you can output, again, +or-1. And you can also have different settings corresponding to different sort of measurement bases of your device. And so if you do this quantum mechanically, then this actually breaks the this CH-SH inequality. And what this really shows is, of course, you know, we're using quantum mechanics, so you might expect that this kind of classical derivation will break down, but in quantum mechanics, you have entangled particles, which basically what this shows is that this is an inherently non-local kind of process. So quantum mechanics inherently has some non-locality, which is why this original CH-SH inequality breaks down. So, you know, this is really kind of thinking about the foundations of quantum mechanics. And this field kind of looks at all kinds of different kind of weird paradoxes, which are things like Wheeler's delayed choice experiments and this Weidemann bomb experiment. You might have heard of some of these things before, and also thinking about why the quantum measurement is the way it is. And so, you know, at the time as an undergraduate student, I really found this a kind of a fascinating type of area, and I really wanted to continue with it. But actually, unfortunately, sort of 2 weeks into my project, due to some circumstances out of my control, I had to actually quit the project. I was told I have to work with a different supervisor. And so I ended up working on some atomic physics problem, which I was less enthused over. And I asked my supervisor, you know, can't I just continue to work on this sort of foundation stuff, which I found so fascinating? But he said at the time, and this is in the early sort of mid-90s, that you know, there's not really any future for foundations of quantum mechanics, and this is basically the realm of philosophy, not really the realm of science. And so, really, at the time, this was kind of an area which was much smaller. People really weren't interested in a broader scale, and was kind of not really taken seriously as a field. But well, as we've seen in the last 20 years, this has really quite changed radically, where now this area of quantum information science, well, basically thanks to the fact that there's a lot of technology that people are now thinking about, and that really has some really great impacts in terms of you know, real world kind of problems. So, but at the same time, the people in this field tend to be kind of interested in this area at the same time. So this is what I really find kind of fascinating about this field. So I ended up, as I said, doing some atomic physics or condensed matter problems in my honors year. And even in my PhD years, I still didn't really go back to the quantum information. I ended up doing some work in particle physics. And the problem which I looked at was to look at this particular model called the Schwinger model. This is a version of quantum electrodynamics in one spatial dimension. So if we imagine hypothetically we lived in a one-dimensional world, not a three-dimensional, three space dimensional world, then this is basically the theory that you would have. And there are a lot of differences with quantum electrodynamics in one spatial dimension. For example, things like Gauss's law. So we're used to the fact that electric fields fall off as 1 over r squared, right? And this is because of Gauss's law, as you learn. But in one space dimension, there's no spread. So basically, all the electric field lines are actually always constrained, and there's actually no spatial dependence of the electric field. So this is interesting as a toy model in high energy physics, because this is very analogous to the effect that quarks have of confinement. The reason why we don't see any quarks flying about in regular, normal situations is that there's this confinement, which means that it's highly energetically unfavorable for lone quarks to exist. So there's this sort of analogous effect. And basically what I did in my PhD was to apply a particular numerical method called DMRG. This is a very powerful numerical method that that was developed, and we applied it to this particular problem. And indeed, we got some, great improvements in accuracy. So specifically, we got sort of 2 significant figures, better than anybody else in the world, which is kind of cool. But at the end of my PhD, I sort of really wondered, well, is life all about kind of getting 2 significant figures over everybody else on a rather obscure model? So while this was actually very interesting, I learned a huge amount in terms of high energy physics, I couldn't sort of help but think, well, isn't there something that I can do that would really impact the real world in a kind of bigger sense? So I decided to sort of go back to this area of quantum sort of foundations information that I was originally interested in. So I went to Japan. I did work with my supervisor at the time as a postdoc was Yoshi Yamamoto. He's a professor at Stanford University and a place in Japan called the National Institute of Informatics. And what we looked at there, and so this is now returning to sort of one of the topics in quantum information science, is this area of quantum simulation. So what you do in quantum simulation is to try and understand quantum many-body problems. And traditionally, this is actually done by doing, well, either, you might do some advanced kind of numerical techniques where, you simulate this quantum many-body problem, or, you do some clever analytics, or, do something like this to try and understand how the system works. But actually, all these are really very difficult. And in fact, many areas of physics today really come down to trying to understand and solve these types of quantum many-body problems. So this idea of quantum simulation, what it says is that, well, instead of actually using these types of classical methods, so if we're trying to simulate it, then we're using a classical computer, or we're using analytical means. It's not inherently quantum mechanical. So instead of that, why don't we use a quantum device to try and understand this quantum system? So, maybe the fact that it's so difficult to understand these quantum many-body problems is because we're using a kind of classical physics to try and understand a quantum problem. So this was basically the observation of Richard Feynman back in 1982. He has this very famous paper where he notices that quantum problems are very difficult to simulate because of this sort of exponential growth in the Hilbert space. So to see that, you just have to look at a n-spin system. If you have n spins, then the number of independent states that you have grows as 2 to the power of n. And so just simply to store the wave function in your regular computer requires a huge vector that's of size 2 to the power of n. And this just immediately goes beyond the capabilities even of modern day classical regular computers, even for the largest high performance computers that you can have, you might be able to go to 40 spins, and this is like nowhere near the size of systems that you might encounter in condensed matter physics, where you have an Avogadro number of spins, right? So this was his actual main motivation of introducing quantum computers. He thought maybe this could be a good way to simulate such systems. And so at the time, this was a relatively new idea. This is sort of in the early 2000s. And there's this paper on the left here where they performed exactly such a simulation, where they managed to make an artificial Bose-Hubbard model. This is a very famous experiment led by the group of Emmanuel Bloch. And what they basically did was to take some ultra cold atoms, and then they used this to make a sort of an artificial lattice. And of course, if you have like a periodic potential, you can make sort of this artificial lattice. They have techniques to do this in atomic physics using so-called optical lattices. And they managed to show phase transition physics in this particular model. So we did something kind of similar in a different system, where we could make these artificial lattices in so-called exciton polarotons. And we observed also some kind of phase transition of a slightly different nature, where there's some condensation in these sort of higher energy orbitals. So if you're interested, you can have a look at this paper. But why this kind of idea is so powerful is basically because it's so widely applicable. So as I mentioned, so many fields of physics actually look at quantum many-body problems. So condensed matter physics, high energy physics, quantum chemistry, all these fields are actually essentially trying to tackle this quantum many-body problem. So if we were to be able to use such quantum technologies to understand this, then this would be really a great breakthrough for many areas of physics, in fact. And it would, of course, help in the broader context, because investigation of such systems basically lead to sort of new materials, new chemicals, and even it can impact sort of biology to some extent if we're understanding molecules at the biological sense. Yeah, so that was kind of what I worked on mainly in my postdoc years. And so after that, I moved to Shanghai. This is where where I'm placed now. And what we do in Shanghai now is basically all kinds of aspects of sort of quantum technologies. Our sort of mainstay is actually this area of using Bose-Einstein condensates for quantum technologies. So Bose-Einstein condensates are kind of like the matter version of lasers. And so we know that lasers are, of course, fantastically useful things in terms of, because they have extremely high coherence properties. So this is sort of the atomic version of that. And one of the good things about those Einstein condensates is that they don't just fly away everywhere, such as light does. So there's many sort of potential applications of the system, which I'll talk about a little bit more later. But being based in China, one of the other types of technologies that we're interested in is quantum communication, because actually currently I think this country here, China, has probably the best technology in terms of quantum communications. And so working in this area is also very interesting. But also we do a range of kind of theory where we're looking at quantum information theory. And we're also setting up an experimental lab to develop a new type of quantum computer, which I'll mention a little bit towards the end of this talk too. So there was kind of a great sea change in the way that everybody was thinking about quantum computers. And this really happened in the middle of the last decade, so between 2010s. decade, the past decade. So before around about the middle of 2000, the decade of 2010, so about 2015 or so, everybody was saying things like, you know, quantum computers, it's going to take 20 years or 30 years to make. This is a interview or a quote from one of the Nobel Prize winners in 2012, Dave Wineland. And so they won the Nobel Prize along with Serge Haroche in 2012 on various aspects of things like cavity QED and ion traps. So in 2010, Dave Wineland was asked this question, which everybody in this field has always sort of asked, of, you know, when will we have a quantum computer? Because I'm promising this for sort of decades and, you know, still don't have a quantum computer. So in 2010, Dave Wineland said something like, at this point, I wouldn't recommend anybody to buy stock in a quantum computing company, but we're optimistic that as technology improves over the years, this quantum computer really will bring unique capabilities. So, you know, obviously it's kind of a rather carefully worded answer, and he didn't really want to make overblown promises. But basically, since around about this paper, which I remember coming out in about 2014, and what this paper showed was that in superconducting qubits, the error rates went actually lower than the threshold for fault-tolerant quantum computing. So what this basically means is that, so you can sort of read here that the single qubit gate had fidelities of 99.92% and 2-qubit gate fidelities of 99.4%. So of course they would have improved upon this since then. But what's significant about that is that the best kind of error correcting codes at the time were, I think in fact still now, around about the 99% fidelity level. And so once you cross that, essentially what happens is that as long as you can build a large enough quantum computer with these fidelities, then systematically the logical errors on the quantum computer will actually be reduced. So so this was really the turning point, I think. I don't know if it's exactly this paper, but there's some kind of, you know, collective wisdom that the field have. And it went virtually, in my opinion, overnight from saying that, you know, quantum computers will take 20 years to, you know, I always knew quantum computers were going to be built. You know, it's just a matter of time. So really around about this time, there was this great, you know, shift in thinking that everybody had. And, you know, these days you start to read articles that are saying that quantum computing, these articles in, you know, financial newspapers saying, how do you invest in quantum computing? And, you know, forget Bitcoin and Tesla. It's all about quantum computing now, and, you know, throw money at it like crazy, which in a way I think is now getting a little bit overheated in my opinion, because, you know, these things always take steady progress. Another sort of interesting development is now people are sort of seriously worried about how quantum computers might be used to sort of hack Bitcoin to some extent. So we analyzed the security risks of this in this paper. This was quite early on, before all this discussion happened back in 2017. So down the bottom here, there's an archive paper you can have a look at. But you know, actually there's wildly different opinions on whether Bitcoin is vulnerable to quantum computers or not. We believe actually the threat is not so imminent, because you really need a very large scale quantum computer to do anything like mining Bitcoin or anything like this. So that and in fact the speed ups there are not really so you know, significant as with for example in Shor's algorithm. So we do not believe it's such an imminent risk, but you know, it's still a fascinating kind of topic. So you know, there's always a worry that people will that people will hype things up so much to the extent that everybody will be sort of sick of hearing about quantum computing and say, oh, okay, this is just a huge bubble. So much so that this is a fake archive article that was obviously not posted by John Preskill, who's one of the major figures in this field. So if you look at the date, it's 2022. So obviously this is fake. But basically what this is saying is that, quantum computing has been overblown, and now we're in this region of quantum winter, which is analogous to the multiple sort of AI winters that field experience. But so I can't tell whether quantum computing will just continue to grow or go through booms and busts such as AI did. But I think eventually, as with AI, now we're really seeing mainstream integration of AI into basically all aspects of our daily lives. Eventually, such a day will probably come, but who knows when that will come? But it's still a fascinating kind of area to be involved in. So just to tell you a little bit more about sort of concrete things that we are actually doing, maybe I just want to spend the last 10 minutes or so and talk a little bit about what we are working on, and perhaps maybe what might interest you most, which is our version of the quantum computer. And this is based on cold atoms. So the technology that we are actually using is atom chip technology. And so what this is a kind of a rather compact way of making cold atom and Bose-Einstein condensate. So traditionally, when you make a Bose-Einstein condensate, what you do is you trap these atomic gases, and you use a variety of different kind of optical and magnetic trapping techniques in order to cool down the gases. And if you cool it down enough, then you can form a Bose-Einstein condensate. But these things, all these things are rather kind of bulky. And if you were to do something like, say, you wanted multiple cold atom clouds, there really wouldn't be a very good way of doing it. And so this is where atom chip technology really comes into its own. So what basically this is it compactifies a lot of the setup that you have for a traditional cold atom experiment and puts a lot of it actually on a single atom chip. So basically all it is actually, it's actually quite simple. It's you have this particular kind of substrate, which you need, kind of rather high sort of cooling properties. So it's usually made of materials such as aluminium nitride, which has very high thermal conductivities. And you pattern sort of wires on the surface of this particular substrate. And basically what that does is to create some particular magnetic fields. And if you apply the right type of fields and currents, then you can create a region where the atoms tend to sort of want to gather in, because it sort of has the lowest energy of this of its surrounding. So this actually is mainly used currently in terms of doing things like quantum metrology experiments, where you want to do precision measurements, and also applications like quantum clocks, atomic clocks. So as you know, atomic clocks, the most precise types of clocks. And so, it's a natural kind of idea that you can use the same type of system, because in an atomic clock, you basically want the atoms to be extremely coherent, since essentially what you're doing is sort of a 1 qubit kind of operation. So you really want very high levels of coherence. And so this atom chip platform is quite perfect for this kind of thing. So just to give you an idea of type of coherence levels that you can have in the system. So in this particular paper reported from 2010 on the bottom left here, coherence times in the region of, say, 1 minute were observed, which is extremely long by sort of quantum various qubit standards. So What we wanted to do was something actually sort of fundamentally different to what a lot of people are trying in the field. So right now, there's many different approaches to quantum computing, and some of the leaders, as I already mentioned, are superconducting qubits. But there's actually many different other candidates for quantum computing, and really, it's actually not clear at this point which is the most viable technology. So we're really at this still early stages of quantum computing technology. And if you think back to the history of regular computing, before we all realized that using silicon and creating sort of integrated chips is the best way to build regular computers, people were building computers out of all different types of devices, such as just mechanical kind of systems and so forth. So I think we're really going through that stage there where we really don't know what is the best type of technology. Everybody's trying something different. Certainly superconducting qubits are one of the leading candidates at the moment, but I think really it's still very early on, and you really can't tell what is going to be the future, what a future quantum computer will actually look like. So, what are we doing that's different to everybody else? So, basically what everybody else is doing is something like this. So if you want to store a qubit's worth of information, then of course what you want to do is you get some kind of particle. So it could be an atom or an electron or a photon, and you store that 1 qubit's worth of information on the one particle that you have. So, whatever platform that you're using. So regardless of what platform that you're using, this is true for basically, I would say, all the leading candidates of quantum computing today. But if you think about it, actually, this is not really what you do in regular classical computing. So this is a kind of a picture of a blow up of a hard disk. So some of you may still remember that there were such things as hard disks in ancient times. And of course, how this works is that you have some magnetized disks, and you have particular domains where digital information is actually stored. So by magnetizing the domains in different ways, you can store a 0 or a 1, right? But of course, this is not consisting of a single atom or anything like that. It's actually a collection of different atoms. And the magnetization, what it does is to kind of hold all the spins kind of together so that it all points in the same direction, so that within one domain, if one atom decides to go rogue and flip, then basically all the other spins around it will try and force it back into its original way. So this kind of has a natural error correction, and this is why actually you don't really need I think error correction at all in classical hardware, because basically nature takes care of that for you. So basically what we wanted to do was just the quantum analog of that. So of course, error correction in a sense is exactly this. So you duplicate your quantum information so that it's actually robust against errors. But we wanted to kind of do a more straightforward, simple approach in order to protect the quantum information. And so essentially what we do is, instead of storing a single qubit on a single atom, we simultaneously store it on a whole ensemble of atoms. And essentially what we're going to deal with is a whole ensemble of atoms at a time. So whenever we want to, say, do some kind of entangling operation, we have to entangle each sort of ensemble to another ensemble, right? So the scheme that we've been kind of thinking of for the last, say, 10 years or so, it kind of looks something like this. So if you have an ensemble of atoms, then we sort of encode our qubit of information in these so-called spin coherent states. These are sort of analogs of coherent states, which you might have learned in quantum optics, but for the spin. So they have very similar types of properties. And we have such ensembles on an atom chip where we've got multiple ensembles, and these types of operations are done ensemble to ensemble. So if you think that this sounds like a crazy idea, then well, you wouldn't be alone. But this is actually not as crazy as it sounds, in the sense that you really can store quantum information and create entanglement between such ensembles. And there have been very well documented experimental demonstrations of this. So for example, here, if you have two atomic gas cells here, if you shine light through both of these, then you can actually generate entanglement. So what basically hasn't really been done in this field yet, so there's actually a couple of different frontiers that we're actually simultaneously interested in. So people have been able to demonstrate entanglement between two atomic sort of ensembles. So this means that they're not degenerate, so they're not Bose-Einstein condensates. But people are sort of edging towards that now, so that when you have a single Bose-Einstein condensate, what you can do is you can determine that, say, the left side of the Bose-Einstein condensate and the right side actually have entanglement between those two sides. So this is a kind of, I would say, preliminary step before really showing that there's actually entanglement between two completely separate Bose-Einstein condensates. And so this is one of the kind of frontiers that people are working on. But also, I think perhaps really where my real passion lies is in trying to get this to work for quantum computing. And the reason why people haven't really approached this is basically because it's actually quite a formidable theoretical problem even to analyze what happens for these ensembles. Because just to make you appreciate that when you entangle two ensembles, you really get some rather complex states. So I don't want to go into a lot of the details here, but for example, in the top line here, we have some operation for qubits where you entangle a qubit. And so basically goes from an unentangled state, like a product state, to some entangled state. So simple enough. But if you have two ensembles, what kind of happens is the dynamics is really much, much more complicated. And you get this in the bottom right graph here, you have this entanglement where it actually shows this fractal kind of nature, which is sort of kind of fascinating in its own right. Who would have expected that an entanglement operation gives some kind of fractal behavior? But basically this happens because of the much more complicated dynamics. And generally people have considered only certain types of entangling interaction, and it generally leads to effectively a kind of a mess. But we have been able to recently work out actually ways of really more systematically emulating the same type of effects that you see with qubits, but with these ensembles, and having this kind of duplication property. So this really requires a lot of kind of theoretical work at the same time of developing the experimental work. And so this is basically what we've kind of been doing at the same time. But because it's sort of fundamentally different from the ground up, a lot of the theory kind of needs to be developed from scratch. So just to quickly say what's on this slide. So for example, one of the key features of entanglement is that if you have entangled state, even in a different basis, so you look in a different basis, it's actually still an entangled state. So if you look at the bottom equation here, this is a singlet state. If you look at a singlet state in another basis, it's still also a singlet state. So there are particular type of states that exactly have this, exactly the same analog in these ensemble systems. So by making use of these things, you can really start to think about doing quantum algorithms. And so what we've been working on are various sort of ways of mapping it onto this ensemble scheme. And actually, these are particular examples, but I think now we already have some general approach so that we don't have to do it algorithm by algorithm. So I think what I was going to talk about here, was to talk a little bit about the latest kind of results on adiabatic quantum computing, but I think I'm sort of out of time, so I might skip these results and maybe just go to conclusions. Yeah, so I think what I want to also just mention, this is a picture of the experimental program that we've also commenced. So this is our 7-trap atomic chip that we have. This is on the right here. It's the same chip, but inside the vacuum chamber. Reason why you can't see the wires is because you have this kind of mirror surface that you need as part of the kind of cooling optics, but underneath that we have this chip. So still, well, in development of this, but I think this will also give some exciting results. So this is the current group. So as I said, we're a sort of hybrid theory and experimental team. So actually, strangely, there's more experimentalists than theorists now. But we're sort of usually split 50-50. And just to sort of summarize, I think, I think this kind of field of quantum information science is a really exciting field that is really developing extremely rapidly. An interesting factor of this is that, normally when you start to do physics, you don't really think about what you might do down the line in terms of what kind of jobs that you might do. If you don't continue with physics, you think you might have to sort of do something else. But now actually a lot of these major companies like Google are really looking for people to do actual quantum physics in the commercial sector. So it's actually interesting that now physics is a real viable sort of career option, even sort of outside of academia. So as I said, we are looking at this sort of cold atom chip technology. If you're interested further, then please have a look at this webpage. And we also launched the YouTube channel. You can just search for that if you are interested in that. I might take this opportunity also to advertise a new book that is coming out later on this year, out from Cambridge University Press. And what this book talks about, basically all the fundamentals of sort of atom optics. So using cold atom systems for looking at various tasks like quantum metrology and quantum simulation and so forth. So there's also a pre-publication version of this on the archive here, which you can have a look at for free. And here are some acknowledgements. So with that, I'd like to conclude, and thanks for your attention.
Thank you, Tim, for a great talk. Yeah, I opened the floor to any questions the participants want to ask. If not, I have a few. So if anyone has any questions, just let me know and I'll allow you to unmute yourself. Duarte, do you want to?
So there's a question in the chat here, right?
Yeah.
Be the most interesting system to simulate quantum mechanics. Okay, so I think maybe this, if I understand the question correctly, so what kind of system that you might want to simulate with the quantum simulation that I talked about? So yeah, I mean, I don't know, the most exciting system, or that could lead to a real world application. that's a bit hard to answer of like, you know, because that's highly subjective. So perhaps I can just give my own subjective kind of direction, which I think is interesting. So one thing that we actually recently did was to simulate the so-called Majorana fermions. So Majorana fermions, I mentioned, I didn't really mention in this talk, but it's one of these systems that Microsoft has been pursuing for quite a long time, because people think that these anionic systems are really highly suited towards quantum computing, because they have these sort of natural error correction properties. So it's a bit of a similar idea to what we're doing, but in a totally different direction, where you let the physical system do the error correction for you rather than you actively doing it. So so we did actually a quantum simulation of a teleportation of Majorana. So, you know, there are no Majorana-based quantum computers at the moment, but of course you can do a quantum simulation of one. And by doing the same kind of braiding gates that you can, that you would be able to with real Majoranas, then you might be able, you can build a circuit to do quantum teleportation of Majoranas. So we actually did a recent experiment that actually simulated this on a quantum computer, and it worked. So I think that's quite a cool result, where you're sort of combining ideas from different areas. But really, I think that there are many different options. So you know, I think I can't really give a number one.
Does anyone else have any questions? Actually, my question was going to be similar on this one, because I work on strongly correlated electron systems, so I'm more or less familiar with this sort of simulations. And you mentioned the Google quantum supremacy paper. More recently, we had the boson sampling paper, and they've shown that quantum computers are really good at solving this very hard problems that would take many years for a supercomputer to achieve. But I don't know if you could just briefly comment on, in terms of an application that not only is beyond supercomputers or classical computers, but actually may have a useful output, if there's any research or any sort of work being done in this direction. Don't know if you want to quickly comment on that.
Yeah. So, you know, it's actually kind of harder than you think. So, you know, even though there's a lot of different, you know, potential applications and algorithms, it's not an, you know, I mean, I think probably a lot of the, you know, your audience would appreciate this, but it's not like, you know, you have a quantum computer and everything runs faster all of a sudden, right? So everything is really kind of specific applications where quantum computers might do something, just some particular task better. So of course, you know, Shor's algorithm, things like that have much more, you know, great speed up compared to classical. But you know, is that you know, that will probably actually break some cryptographic protocols more than actually, you know, help to create certain things. But yeah, well, in terms of applicability, I think this is why so quantum simulation, really, people I think really are excited about that, because that really does seem like a door that people can, you know, go towards to really examine quantum materials in a completely new way. So I think that that's always quite a major direction. I mean, quantum metrology, I didn't really talk about that, but doing precision measurements, I think this is already something that you can really think about applying in many different contexts. So I mentioned the gravitational wave, but actually that general principle applies to many different types of precision measurements. And of course, quantum cryptography is also huge as well. So, you know, secure communication. So in terms of quantum algorithms, I think it really, you know, it's always going to be slightly niche kind of applications, but I think, you know, another direction that a lot of people are looking at is quantum machine learning. But even then, I think that has its own problems because actually encoding the information into the quantum computer is actually a major problem that people really don't know how to do. So that also is not like an overnight applied to everything type of thing. But so I think in terms of the real world things, in fact, all these other things like cryptography and simulation and all these things might be much closer to real world applications than the quantum computing. But, you know.
Yeah. Okay, so we have a question from let me just find you on the...
Yeah, so there's another chat question here. Yes, so the question is, how about simulation of complex systems and networks like transportation networks, social networks, even protein folding? Yeah, so I mean, the immediate answer that I would say is, you basically just use Grover's algorithm for all these types of tasks. So essentially, I think a lot of what you mentioned here boils down to some kind of search problem. So it's optimization, right? But I mean, I think even there, I really don't want to mislead people to just sort of say that, oh yeah, everything's going to be much faster just applying with the quantum computer, because I think actually it's not always the case. Because so, for example, in Grover's algorithm, you get a quadratic speed up, right? But in a lot of these problems that you mentioned, these are problems that scale exponentially, and then the square root of an exponential is still an exponential, right? But it just, in the exponent, there's some factor of a half now that, of course, that helps a lot, but it's still exponential. So then you have to compare that to the best classical algorithms, and classical computing has been around for a long time, and people have been developing very clever heuristic algorithms to do search problems and things like that. And so basically it's a question of, okay, is that half that you get from Grover, is that going to be better than the factor that you have in your best classical algorithm? And then it's really case by case, right? So in some cases, just using Grover might already beat the best classical, which is great, right? But that might not always be true. So then, it really depends. So again, it's just quantum computing. It's not going to be something that just speeds up everything, but in some cases I think it can. And I mean, this is why developing more quantum algorithms is also a really interesting area.
Thank you. Any other questions? If not, then I'd like to thank you, Tim, once again for having accepted our invitation and for a great talk.
Pleasure.
Thank you.
Okay. Oh, there's another question, but
is that
are we out of time? Or, yeah.
I mean, we have time if you have time.
Okay. Yeah, sure. Yeah.
So do you have another question? I think you should be able to unmute yourself. If you...
Hi.
Oh, yeah.
Hi,
Hello.
I'm So.
Hi.
Thanks for answering the previous question. Yeah, it's really an interesting talk. And I'm about to get started on like a project relating to superconducting qubits. So I think this talk is like really timely, I feel. Yeah.
Great.
So I was wondering, right? I mean, where I am doing research, I see that it's either like you're doing theoretical or experimental physics. But I see that for in your case that you're actually doing both, like working in both areas. So I'm wondering, what's it like to be working with both theoretical and experimental aspects of quantum information and technology, and if there's any advice on how we as undergrads can prepare if we want to do both things, I guess. Yeah, not just purely
Yes,
theoretical
yes. So generally, it's very kind of difficult to do both, and the fact is that you know, if you start going down one path, then you're probably only going to be employed in that one path, right? So you know, I started off in theory, and I really cannot really say now that I really know anything so much about experiment. I mean, so in terms of running this lab, you know, I basically hire somebody that is very knowledgeable about this, about the lab, just to set it up. And so I think, generally speaking, you know, you really probably do have to specialize in one of those directions. And, you know, perhaps if you sort of do both, you might actually, you know, it might sort of water your sort of knowledge base down. But at the same time, I really was very excited to go into this experimental area because, you know, this field is really about kind of making technologies, and, you know, you can really make some great contributions in theory, but if you really kind of want to make a big impact, I mean, there's really nothing like actually building it and saying, look, we've made it, and, you know, here it is, and, you know, you can look at it. You know, that really has such a great impact, so that, you know, I think we really didn't want to sort of pass that up. So that's why I really wanted to go down that direction of kind of doing both. But I think, you know, it was kind of due to kind of some unique circumstances too. I think being in China for myself helps because, you know, there are sort of more opportunities here for doing this kind of research, and it's very much encouraged. So it kind of depends on your circumstance too. So I think it's not a really easy kind of route to do both, but of course, scientifically, it's extremely interesting, and I think it can really have a big impact if you manage to pull it off. So yeah, so I hope that answers your question. I'm not sure if I really completely said maybe what you want to hear, but I think that's my opinion on it. Yeah.
Okay, thank you. Any other questions? If not, yeah, I think that's it. Thank you once again, Tim, for
thank you.
a
very much.
Great talk. And with that said, I think we can close this session. Thank you.
Okay. All right. So thank you, everybody. Yep. Okay. So. So I'll stop share there, and okay, so I'll leave the chat. So okay, so thank you, Pedro, for everything. Yeah, it's a great opportunity. Okay. Okay, so see you later. Bye.
Yeah.